Okay. So last time we have discussed the grand canonical ensemble, which is the way to describe systems where which are in chemical contact with the largest system, and so which can exchange the particles. And so we have seen that, so what we have to do in order to compute the properties, statistical properties in the grand canonical ensemble is first to compute the grand partition function, the grand canonical partition function, which is the sum over all the number of particles. The fugacity is small z to the power n times the canonical partition function for a system of n particles at temperature T and volume V. Okay, so once you have computed this quantity, then you can compute the thermodynamics by the relation P as a function of chemical potential, volume, and temperature is equal kT by the V times the log of the grand canonical partition function. Okay, so this is so this is the recipe to compute the thermodynamics. So we have. So what I want to do today is to show you that this description is particularly useful to describe phase transitions. Okay, and we are going to do that in say using a very simple and stylized model of a situation where you have a solid and the vapor which are in coexistence. Okay, so we think the system at fixed volume V, where there is some solid, and here there is some vapor. And of course, you have exchange of heat and particles between the two systems. And okay, so for the vapor, we are going to take a very stylized description, which is to say, we assume that this is an ideal gas. An ideal gas, we have seen that the grand canonical partition function. So we have seen that the canonical partition function is 1 over n factorial times the partition function for one particle to the power n. And this Q1 of T and V is equal to V times a function of the temperature, which, to be precise, for a classical gas, monatomic gas of particles with mass m is given by, and there is h bar squared here, right? Okay. So then the grand canonical partition function for the vapor is this 1 over n factorial is because particles are indistinguishable, so any different configuration where I interchange particles should be counted as one configuration. So if I take this formula here, then I have that the grand canonical partition function is just the exponential of z times q1, which is e of z times, I call this function f of t, okay, times v times f of t. Okay, so this is, and then we have seen already last time that if I compute the pressure, this is kT divided by the volume, and then I have to take the log of z, which is just z times v times this f of t. But then I can also compute the number of particles, which is just z times dz of log of is big Z. And log of Z is just this. So this is just ZV times f of t. So using this, this is just equal to n. Okay, so we have n kT divided by v. So this is our old friend, the classical ideal gas. Okay. Now, very good. So now, if this n here or this n here is actually the number of particles which are in the gas phase, right? So there will be a number of particles which are in the gas phase, but these are in equilibrium with the solid. Okay. So there will be a number of particles in the solid phase, and these two are should be in equilibrium. Okay. So this is our this is the vapor. What about the solid? For the solid, we are going to say that so our model for the solid is that the solid has a crystalline structure. Okay, where atoms sit on the sides of a regular three-dimensional lattice. And what these atoms do is to make a small fluctuation, small harmonic fluctuations around their equilibrium position. So we model this this solid as a gas, as a system of harmonic oscillators. Okay, classical harmonic oscillators. And so the partition function for the solid is this time is just the partition function for one harmonic oscillator to the power n. There is no n factorial because all the microstate of the system, in all the microstates of the system, the atoms are fixed in their positions. So the atoms are distinguishable by their position. Okay, there is a label on each atom, which is the three-dimensional position. Okay, and we have seen that the partition function for one of these harmonic oscillators is the canonical partition function for one of these It's very easy to compute and is kt h bar omega to the cube, because now I assume that each atom can have 3 modes of oscillation. Okay. Very good. So then my canonical partition function is, if I use this formula here, this turns out just to be the geometric series. And if I call this function phi of t, then the grand canonical partition function is 1 minus z times phi of t. And from this you get that the pressure is kt over v times the log of 1 over 1 minus z phi. And if we eliminate, if we compute the number of particles as before, we find that this is kt over v times the log of 1 plus the number of particles in the solid. Okay? And then you can derive all the thermodynamics. Now, what is the condition of equilibrium between the solid and the vapor? It's the chemical. What is so the chemical potential must be equal. Okay, so chemical potential must be equal, and also the temperature must be equal. Right? Very good. So this means that the fugacity must be equal. Okay, so the fugacity, which is e to the beta times mu in the gas, must be equal to the fugacity in the solid. Okay? And so from this equation here, you find that the fugacity in the gas is equal to the Ng divided by V times F of T. And this must be equal to the fugacity in the solid, which when you solve for the number of particles in the solid, you have to take z times the derivative of log of z by z. And this is z times 1 minus z phi, and then times phi. Okay, so if you eliminate, if you solve for z in this equation, you find that z times phi must be equal to n of the solid divided by 1 plus n of the solid. Okay? So z of the solid is 1 over phi of t times ns over 1 plus ns. Okay? So this is essentially equal to 1. So this 1 is much less than ns. Ns is of order 10 to the 23. So this is essentially equal to 1 over phi of t. So the condition is that the density of the gas is equal to f of t divided by phi of t. Okay? And if you use the equation which we have written there, this is 2 pi m kt to the 3/2 divided by h cube times phi is this one, kt cube h bar omega also cube. So this is equal to 2 pi m divided by kt, this and this. Then h bar, so this is so there is a 2, so the 2 pi goes downstairs, and then you have omega squared here. So the final result should be that this is equal to, let me write it here, is m kt m omega squared divided 2 pi kt to the power 3/2. Okay? If I did everything right. Okay? So now, yep.
Why omega squared? Oh, yeah, that's right.
Omega squared, because that's, yeah. So now it is convenient. So how many? So how does this thing behaves? So the density of the gas is a function of temperature. So this temperature of the gas, you see, goes down. The temperature increases, this goes down. So it means you increase, yes, you sorry. So the is this right? Huh? This is a bit disappointing. Huh? So let me see. Yes, so this is a bit disappointing because the temperature, the density of the gas should increase as you increase the temperature, right? There should be more particles which go into the gas phase. Okay, so it means that one of the two models must be wrong. Okay, and so one model which is wrong is definitely the one of the solid. Yes?
Are we treating a different way the volume of the gas and the solid?
Sorry?
Are we labeling different for the volume of the gas and the solid?
You mean this? No, the you mean that we should need an factorial also here?
No.
No.
The volume. Is it different?
No, the volume is the same. Is the same, no? Because what we are saying is that so at this chemical potential, the gas will occupy this whole volume. Okay, so say I'm drawing this picture in this manner, but okay, no. So what happens is essentially that in this model, the volume of the solid is 0 compared to the volume of the gas. Okay, because see the gas so when or if you want the variation in the volume of the solid with respect to the variation in the volume of the gas, when you change the number of particles, is negligible. Okay, because yes, because so yes, you can think about the mechanical equilibrium about these two systems, and you see, if they are in mechanical equilibrium, then the pressure also will be the same. So in order to derive the description in mechanical equilibrium, we have to also make a Legendre transform and have a description in terms of P instead of V. Okay, but mechanical equilibrium will tell you that if you have so you see, for a change of so V times P is very small, okay? Which means that essentially, if you have at constant P a change in V, then you need in order to have Yes, essentially the density of the gas of the solid is much larger than the density of the gas. So if these two numbers are comparable, this means that the volume of the solid is very small compared to the volume of the volume of the solid is very small compared to the volume of the gas. Okay, so in this model in this approximation, this will be 0. Okay, so now in this model, essentially, the problem is that we get a very unphysical result. And this is because the model of the solid that we are using is a bit is not very realistic. Okay. In particular, there are too many independent modes of vibration of the solid. Okay. So if you consider a realistic model of a solid, you would have a more realistic model would be of atoms which are tied one with the other with harmonic forces. Okay. So and of course this is a completely different model, but what you can anticipate is that out of this there will be only of the three modes of oscillations. So essentially only one can be described in the way I have described here. Okay, so this is probably something you will probably have done this in solid state physics, the Debye model and the Einstein model for a solid. Okay, so essentially, so what you can imagine is that so if we had taken instead of this model a model where the oscillation of one atom were measured by only 1 degree of freedom instead of 3, then this phi of t would have been just kT divided by h bar omega. Okay. And then what you would have had is that ng divided by v would have been a function, would have been essentially a constant times f of t is proportional to kT to the n over 3 divided by kT. This would have been the square root of kT. Okay. And so you would have something like this, okay, which is more realistic. Okay. Now, of course, this model, if you have a total number of particles in your system, then you will have at a certain temperature, all the gas will go into the solid phase if you decrease the temperature, and this is where essentially this curve essentially hits the the, 2 the density of the solid, right? So this solid will have a certain density, so this will give you the phase transition, okay? So of course, so as you can see, these two models are very, very stylized, too much stylized for describing this phenomenon. But the point you may take out of this exercise is that the grand canonical ensemble is what you have to use if you want to study a system which is in chemical equilibrium, which can exchange particles from one component to the other. Okay. Okay, so actually, if you when you use the grand canonical ensemble, we have seen that you can work with a chemical potential fixed. Then you can then you can compute an equation for the number of particles, and then from this you can eliminate the chemical potential as a function of the number of particles, and you can derive a description in terms of temperature, volume, and number of particles. Okay. Now, this description must be equivalent to the description we have derived previously from the canonical ensemble. Okay. And this is only possible if the number of particles, the fluctuation in the number of particles from one member of the ensemble to the other are very, very small. Okay. So it is important to compute the fluctuations of the number of particles in the grand canonical ensemble, to see when is it that these fluctuations are really small. So we have said that the number of particles can be computed as derivative with respect to the fugacity of log of the grand canonical partition function, because well, this is nothing but the sum from n equal to 0 to infinity of small z to the n partition function of temperature T and B times z divided by the same thing. Okay, so this is when you take the derivative of z with respect to the log, you get 1 over z, which is this, and then the derivative of this with respect to, n. The derivative of this with respect to z gives you n times z to the n minus 1, and if you multiply by z, you get z n to the n. Now, if you take a second derivative of this with respect to z, to the fugacity, if you take a further derivative of z with respect to this, then what you have is that you can, if you take the derivative up here, you have another n which comes out. So there is n squared z to the n times qn divided by the same thing. And then there is the derivative when you take the derivative down here, and essentially you get minus z squared, so the grand canonical partition function squared, times this times the derivative of this, which is essentially this object squared. Okay. Okay, so, and now you look at this expression, and you see this is the expected value of n squared over the grand canonical partition, over the grand canonical ensemble, and this is the expected value of n squared. Okay, so this is precisely equal to the square fluctuation of the number of particles. Okay, and so this is exactly n squared minus average n squared. And actually now, so you see that you can relate this to thermodynamics now. Okay, so this relation here is not particularly transparent. So let us try to derive a relation which is more transparent than this. But first of all, notice that if you compute the relative fluctuations, the square of the relative fluctuations, so average n is just n squared, then so you see that this is kt divided by n squared times this derivative here, which can be written, yes, this, so this object here can also be written as kt times the derivative of n with respect to mu at constant t and v, no? Because I remind you that z is e to the mu divided by kt, and essentially this z times derivative of z is like a derivative with respect to log of z, which is 1 over beta times the derivative with respect to mu. Okay, so this implies that z derivative with respect to z is essentially the derivative with respect to log of z. And since this derivative is taken at constant kt, constant t, then this is just kt times derivative with respect to mu. Okay? So you get this relation. So this, the relative fluctuation can be written as now you see, the first thing you find is that T and mu are intensive quantity, n is an extensive quantity. So this relative fluctuation will be small, will be of order 1 over n. Okay, so the relative fluctuation will be small. So this is why the description which you get in the grand canonical ensemble will be equivalent to the description which we have in the canonical ensemble, where the number of particles is fixed. Okay. Now, still, we want to find out when is this coefficient large. In order to do this, we do a little bit of manipulation based on thermodynamics. So first I introduce the relative volume, which is the volume per number of particles. So instead of working with n as a variable, I work as a function. I consider a v as a variable. So this means that this relative fluctuation by n squared can be written as kt over v squared times v squared, because n is v divided by small v, times now here I have the derivative of v over small v by mu at constant t and v. So v, since v is constant, I can take this v out. So, and this is just kt divided by v, 1v cancels. And then the derivative of 1 over v by mu is 1 over v squared, is minus 1 over v squared, and the derivative of small v with respect to mu. Okay? So I have a minus sign times the derivative of v with respect to mu at constant t and v. Okay, so this is still not particularly transparent. So, in order to make it more transparent, one can use the thermodynamic relation that d mu is p dv minus the entropy density times dt. So how do you derive this relation? So we have seen last time that you have a general relation in thermodynamics which you derive from the extensivity of the entropy, which tells you that St minus plus mu n minus E minus PV is equal to 0. Okay? Now, if you want to describe a system in terms of the value, so if you want to find the thermodynamic potential at fixed pressure, number of particles, and temperature, is the Gibbs potential. So what you have to do is to do a Legendre transform, right? In a Legendre transform, you have to take the free energy, the Helmholtz free energy, A, and from this you have to add PV. Okay? So this is E minus Ts is the Helmholtz free energy plus PV. So from this, you see that using this relation, E plus PV minus Ts is exactly equal to mu n. So you see mu is an intensive variable, so it does not depend on n. So this tells you that mu is a function of P and T. Okay. And then of course, the differential of mu will be will be equal to P times. So you get the differential of mu from the differential of G. So you have P times dV. Sorry. It's V times dP minus S times dt. Okay, which is this. Now this tells you that sorry, V dP. That effectively I can at constant temperature I can in any transformation I can interchange a derivative with respect to mu by 1 over V times a derivative with respect to P. Okay, so what I can do is to write this as minus kT over V times 1 over V times the derivative of V with respect to P at constant T. Okay, so now minus 1 over V times this derivative is what is called the isothermal compressibility coefficient. So you can write this as kT divided by V times the isothermal compressibility, where kT is number kT is minus 1 over V, derivative of V with respect to P at constant temperature T. Okay? Okay, so when is this coefficient large? So it is, if you think at one situation where it is large, is precisely when you have phase transitions. So if you have a phase transition, if you consider a gas and a liquid in equilibrium, then you can draw isotherms in the VP plane. Okay, at high temperature, at high temperature you have PV is equal N kT. So these are just hyperbolas, right? Now, if you lower the temperature, you will start to get closer to the temperature where there is a phase transition, liquid solid, liquid gas phase transition, and effectively what will happen is, so at the liquid gas phase transition you will have below the liquid gas phase transition, you will have something like this. So you will have at a given temperature, so if you consider the phase diagram in T and P of a substance, you will have the three phases which are like this, solid, liquid, and gas, or vapor. So this is the critical point. So if you are drawing isotherms at very high temperature, there will be no distant difference between liquid and gas. So you will have just something which is well approximated by the ideal gas law. So as you, if you are at this transition below this critical temperature, you will have that there is a pressure. There is a particular pressure, which is this one, at which the gas will start turning into liquid. Okay, and so so you see at the phase transition, you have the pressure as a function of the volume is flat. So the derivative of the specific volume with respect to the pressure is infinite. Okay, so and as you if you draw isotherms which are very close to the phase transition, you will get something which is with a slope which is very close to 0. Okay, it means that this coefficient will be very, very large. Okay, this coefficient will be very, very large. So it means that if you want to discuss phase transition, you cannot use a canonical ensemble, because the fluctuation in the number of particles of your system become large, and then you need to use the grand canonical ensemble. Okay. Now, what about the fluctuations of the energy? So also the energy is not fixed. So we have seen last time that in the canonical ensemble, the fluctuations of the energy are related to the specific heat. And what is the equivalent relation in the grand canonical ensemble? So the fluctuation of the energy in the grand canonical ensemble, again, you can write a formula which is exactly equal to the one I wrote previously, because you can relate it, if you take twice the derivative with respect to beta of log of the grand canonical partition function, you see that this will produce exactly the fluctuation of the energy exactly by the same calculation, because every time you take a derivative with respect to beta, you have a factor of E which comes down. Okay, and now this is really minus the derivative of the energy with respect to beta. However, this is a function of the chemical potential, the temperature, and the volume. So this is taken at constant fugacity and volume. Okay. Now, if we want to derive a description instead where the if we want to eliminate the fugacity from this formula, we can use the fact that so you can think of the energy as a function of temperature or beta, and the number of particles and the number of particles, which is a function of beta, okay, and z is fixed, okay. So if you keep z and v fixed, when you change the temperature, not only the energy will change, but also the number of particles will change. Okay, so you will have that this is the change in the energy at n and v fixed plus the E dn at z and v fixed times dn d beta. Okay? At z and v fixed. Okay? Now for dn d beta, we can derive an equation for that. So dn d beta at constant z. So this is the derivative with respect to beta of the derivative with respect to log z of log of the grand canonical partition function. Okay, so and I can interchange the two derivatives. So this will be the derivative with respect to log z of the derivative of z with respect to beta, which is minus the energy. Okay. And now this derivative has to be taken at constant t. So this is kT times the derivative of E with respect to chemical potential at constant T and V. Okay? So this means that I can write this as dE d beta at constant N and V plus dE dN at constant Z and V times kT dE d mu at constant T and V. Okay? But now I can also write that the derivative of this. So if I keep so this derivative of energy with respect to mu, I can write it as the derivative of E with respect to n times the derivative of n with respect to mu. Okay? And okay, so now if I sorry. Yes, so here what I'm keeping fixed is again T, no? Because I'm considering the energy as a function of temperature and number of particles. And well, so this is the EDN at constant T. So you see, if I put all these things together, what I have is that yes. So sorry, KT, dnd beta. Yes, okay. So, and the last thing is that this dnd mu, we have already said that this tells us the fluctuations of the number of particles. Okay. So the nd mu is 1 over kT times the fluctuation in the number of particles. Okay. Now, if I put all these things together, so what you can see is that so I will have the derivative of E with respect to T times kT squared at constant N and V, plus the derivative of E with respect to N squared at constant T and V times the fluctuations in the energy, in the fluctuation in the number of particles. And now you see this is exactly the formula for the fluctuation of the energy at constant N in the canonical ensemble. So these are this is precisely the fluctuation of the energy when N is fixed, plus dE dN squared, the constant T and V, times the fluctuations of the number of particles. So you see, this result tells you that there are two contributions which contribute to the fluctuations of the energy. One is the fluctuation in the energy at constant N, and the other thing is that the energy depends on the number of particles, and the number of particles fluctuates. Okay, so this is what you expect if in the grand canonical ensemble the energy and the number of particles fluctuate independently. Okay, because if the So if they fluctuate independently, then the variance of the energy can be expressed as the sum of the variances. Okay. But so this statement tells you that in the grand canonical ensemble you consider independently energy and number fluctuation in the number of particles. Okay. Okay. So, are there questions? Is everything clear? Sorry? Okay, so you remember we derived the fluctuations of the energy in the canonical ensemble, and we found that they were described by this formula, right? So what this formula tells you is that when you consider the fluctuations in the energy, there are two terms which contribute to the energy, to the fluctuation of the energy. The fluctuation of the energy when the number of particles is fixed, which is the same as the one we computed in the canonical ensemble. This is related to the specific heat at constant volume, right? Of a constant volume and number of particles. But then there is also a part of the fluctuations in the energy. So the energy also changes because the number of particles change. And then the fluctuation in the energy is related to the fluctuation in the number of particles. Okay, so this formula which we have derived tells you precisely this. Okay, in the canonical ensemble you have an additional source of fluctuation in the energy, which is due to the fact that the number of particles also fluctuates. Okay. So yes. So if you want, you can consider this as the specific heat at constant chemical potential. Well, instead of fixing the number of particles, you fix the chemical potential. And it will be larger than the chemical potential at fixed number of particles. This is the same reason why the specific heat at constant pressure is larger than the specific heat at constant volume. Because when you heat a system at constant pressure, it will also change the volume. So there is a work which the system will do, and that is also to be taken into account in the change of energy, right? So if the volume is fixed, it will not do work. So the change in energy will be just the change due to the change of temperature, okay? Or the heat. In this case, so the energy, the fluctuations of the energy are always related to the specific heat, in this case at constant chemical potential. And when you heat the system, it will also do chemical work, because it will exchange particles with the heat bath. Okay, and you have to take this into account. Other questions? So if everything is clear, then in the last lectures, I would like to discuss more in detail quantum statistical mechanics. And in particular, what we will do is to discuss in general how you generalize this notion of ensembles from the classical case to the quantum, specifically to the quantum case, and then discuss some simple systems such as ideal gas, ideal quantum gases. Okay, so this is the program for the next for this week and the next. Okay, so now imagine that we want to repeat all our derivation in the case of quantum mechanics. Okay, when we consider that our system is really quantum mechanical. So if it is quantum mechanical, then the state of our system is described by a wave function. So this wave function can be written in the position representation, so where Q is the collection of positions of all particles. But you can also generally describe it in terms of any other state, any other basis. Okay? So are you familiar with this notation? Okay. Very good. So now the idea of statistical mechanics is again the same. So what? So the idea is that we have a macroscopic system. So we observe a macro state, which is specified in terms of few variables, such as number of particles, volume, and energy, or temperature, or chemical potential, etc., etc. And we want to relate this macro state to a collection of microstates. Okay. In particular, we want to relate this macro state to the property of an ensemble of systems, each of which is in a different microstate, but whose distribution on the space of possible microstate is consistent with the macroscopic state we are interested in. Okay. So what we have to do is to introduce the notion of ensemble. And in the quantum case, since each state is described by a wave function, an ensemble will be a collection of wave functions. Okay, so an ensemble will be a collection of wave functions, where this k will go from 1 to this curly n. Okay, which is in principle infinite. Now, of course, how we describe what are the properties of this ensemble will depend on what are the physical properties of the system we are interested in. But quite generally, you should think of this wave function as the different points in phase space. Okay, or the different points in the phase space, and what we want to find is an analogous of the density in phase space, which is appropriate for a quantum system. Okay. So the way to do this is, so first let us introduce a general orthonormal basis. So each of these functions, psi k, can be expanded in a set of orthonormal basis. Of course, this will also depend on time. And so these psi, these phi are, say, for example, eigenstates. Well, in general, there will be a set of orthonormal bases which describes my Hilbert space. Okay. Now, and of course, the time evolution of these coefficients here will be given by the Schrödinger equation. Since for each of the state will evolve with the same Hamiltonian, H. Then this implies that A H bar A K N dot this this will be equal to since this A K N of t, I can write it as the integral dq of C n star q times psi k of q and t. Right, so if I take a derivative here, AH bar times time derivative here, I will have AH bar times the derivative of psi k, which is H times psi k. So what I will have is the matrix element of the Hamiltonian between state n and m prime. We will have a sum over m. The matrix element of the Hamiltonian between states n and m times a m kt. Okay? This is just basic quantum mechanics. Now, the way, of course, quantum mechanically, you can think of these coefficients as the probability amplitude. So this will be the modulus square of this object here is the probability that if I look at the point k of the ensemble at time t, it will be in state n. Okay. Now I am interested in averages over the whole ensemble. Okay. So it is convenient to introduce the density matrix. And the density matrix is an operator. And it is an operator which has the matrix elements of these operators are equal to an average over the ensemble, the sum over the copies of my ensemble of A star M of t, A n of t. Okay. So if you want, you can also write it this as 1 over n sum over k times psi k psi k. Okay, so if you if you take this expression here and you compute the matrix element between state n and m, you will find the formula above. Okay, so for now, so for example, if you you see that if you compute the diagonal elements of the density matrix, this is precisely 1 over n somewhere k a n t modulus square. So this is precisely the probability that in a copy, so there is a k here. Is precisely the probability that I will find the copy k in state n averaged over all the copies in the ensemble, over all the points in the ensemble. Okay. So in this, the idea of this density matrix is that it encodes two types of averages, one over the quantum state and the other one over the ensemble. Okay. Now, what are the properties of this density matrix? So one property is that, of course, since I have that the states are a complete basis, so this is equal to 1. So if this is a complete orthonormal basis, then the sum over all the states of the amplitudes modulus square it must be equal to 1. Then you can see that also rho n, and if you sum over all the states, the probability to find it in state to find the state in state n, then this is equal to 1. Okay, so it's a normalized. So the diagonal elements are normalized to 1. So the other important property of the density matrix is its evolution. Was there a question? No. Okay. So how does the density matrix evolve? So the evolution of rho. So if I take IH bar times d rho dt, then I have 1 over n somewhere all the copies, and then I have two terms. I have a star k n. So let's do it for matrix element n m. So dt times a star m plus a n k. So this is always k star. Okay, a n times d a m k star dt. Okay. This is just I'm just taking the time derivative of the two parts. So this is equal to so there is a I h bar, of course. So I h bar times this is equal to I h bar times dAn dt is, as we said, sum over m right? So if you use, and of course for the complex conjugate, I will have a minus sign, no? I h bar times the complex conjugate will be a minus sign, and the complex conjugate of m. Okay, so if so here you have a sum over k, a sum over m times h n m a k sorry, so this I have to call it m prime a m k star minus h n m prime and then a n a k a m prime k star. Now if you and this is m prime m prime, okay. Now you see, so there is this sum over m prime which can go outside. So and you will and you have sum over m prime of 2 terms h of n m prime times what I have here is exactly rho of m prime times m, and the other term is rho n m prime times h of h of n prime m because yes, when I take the complex conjugate of this, I have h star m prime, and this is h m prime m, okay, because h is a Hermitian matrix. Now you see this is exactly the nm matrix element of the commutator. Okay. So what you see, what you get from this is that this object is precisely the commutator of rho of h rho matrix element n m, which tells you, sorry? So the 1 over n goes in the definition of rho. 1 over n sum over k of this object gives you the rho n m prime. Okay? Sorry. So this is a quite important result because it tells you that I h bar d rho dt is equal to h rho. So and this is exactly the same expression. This is the form of the Wheel Theorem. If you remember, we discussed the Wheel Theorem where we were discussing classical systems. And Wheel Theorem was telling us that the evolution of the rho dt was so what this equation is telling you is that if you look at the stationary state, so at a stationary ensemble, so an equilibrium state, in an equilibrium state you must have that rho is a function of h. So the density matrix must be a function of h. And this is exactly the same statement as Wheel theorem. Okay? So from this point onwards, essentially you can derive all the ensembles we have discussed in these days exactly in the same way, because now we know that rho is a function of the Hamiltonian. So what we have to do is to find what type of function is appropriate for different type of physical conditions. Okay, when we consider isolated system, when we consider systems in thermal equilibrium, or when we consider systems in thermal and chemical equilibrium. Okay. Okay, so this is what we will do next time.